Now let's work on a beam example to understand how to use the stiffness matrix to solve a beam problem using finite element method. We want to work on this example. A beam which is fixed at one end, and halfway in the length of the beam we have a force, a constant force F applied to it in the negative y direction. And at the free end of the beam we have moment M applied in the counterclockwise direction, which would be positive. The total length of the beam is 2L, so the length of the section of the beam between 1 and 2 would be L, and the other section would also be L. We want to consider constant E and constant I. We can discretize this beam into two elements, as I've shown here. Between 1 and 2, I'll have element 1, and between nodes 2 and 3, I'll have element 2. And for each node, I will have its moment and rotation, force, and displacement. Again, if I write phi 1z of 1 with a hat, it means that it's the rotation of beam or of node 1 at element 1 in z direction or about z axis in local coordinate system. Node 2 is common between elements 1 and 2, so it has two moments and two rotations, two forces, and two displacements. Similar to what we did in trusses and what we did for the spring as we were studying the stiffness matrix, we will have to use equilibrium and continuity to use these two local nodal forces and local nodal displacements to find its global counterpart or global format. So for element 1, I have nodes 1 and 2, and I can write the stiffness matrix just like what I found for a typical beam element. I put 1 in here to refer to element 1, and the hat means it's local. And what it does is that it relates the local nodal forces to local nodal displacements. So we also call the M's and Phi's forces and displacements here, but basically what I'm talking about is that this is a vector of forces and this is a vector of displacements, and Phi is in the category of displacement while M is in the category of forces. And I can relate the two vectors with the stiffness matrix, which is a 4x4. Next I have element 2. It's very similar to element 1. The only thing is that I have to define that at element 2, and now the forces are defined for node 2, and so are the displacements defined for node 2 at element, or node 2 and 3 at element 2, and node 2 and 3 at element 2. So the goal is to move from the local coordinate system to global coordinate system. I have these two equations that relates the local nodal forces at element 1 to local nodal displacements at element 1 with the stiffness matrix of element 1, and the local nodal forces of element 2 to local nodal displacements of element 2 using the stiffness matrix of element 2. Again, node 2 is common between the two elements, so I have forces that I have to deal with. I also have displacements that I have to deal with to make this equation. 6 nodal forces, 6 nodal displacements. So I have 3 nodes in my example, and each node has 2 degrees of freedom, which is D and Phi. As a result, I'm looking for a 6x6 big stiffness matrix. Before I move on, let's use equilibrium and continuity. From equilibrium, I can say that the local forces at node 2 summed together would give me the global force at node 2. The summation of local moments at node 2 from two elements gives me the global moment at node 2. Since node 1 and node 3 are not attached to other elements besides element 1 and element 2 respectively, they're easily, their global formats of forces is basically equal to their local forces, and the global forces at node 3 are equal to their local counterparts. From continuity though, I can say that the global d2y, which is displacement of node 2 in y direction, is equal to the displacement of node 2 in y direction of local of element 1, and that is also equal to the local of element 2. And the same is true for the rotation of node 2 in the global coordinate system and its relationship with the local rotations. Again, since node 1 is only attached to element 1, I have these simple equations or relationships between the local and global displacement of node 1, and node 3 is only attached to element 2, so I have this simple relationship between the local and global displacements of node 3. Now I have this 6x6 matrix to fill in. I have the global forces, 6 of them, and I have the global displacements, the 6 of them. And I have written on top of each column its corresponding displacement vector or element in the displacement vector. So d1y, phi1z, d2y, phi2z, on and on. And next to each row, I have its corresponding element in the displacement vector. Next, we'll move to fix this or make this big 6x6 matrix using the local SFS matrices that we found earlier.